right, get ready, because we're taking a deep dive today, and you know it's going to be a good one.
Oh, yeah, definitely.
Because you guys have sent us excerpts from Quantum Mechanics, the Theoretical Minimum.
By Leonard Susskind.
Yes.
Yes. And Art Friedman.
And this stuff is fascinating.
It really is.
Our goal today is to try and give you a solid understanding of the core principles of quantum mechanics, even if you've never encountered it before.
It's a great book for that. Really breaks it down.
Yeah.
In a really nice way.
So let's just jump right in.
Okay.
One of the first things that the book emphasizes is that quantum mechanics is not just classical mechanics on a smaller scale.
Right. Yeah, it's not just miniaturization.
Yeah.
It's a completely different set of rules.
What are some of the key differences that the book highlights?
Well, one of the most fundamental ones is how we use abstractions.
Okay.
So in classical mechanics, we visualize things. So, for example, a spinning electron. We might visualize that as a tiny sphere rotating on its axis.
Right.
But in quantum mechanics, that picture just doesn't work.
So how do we think about an electron's spin in the quantum world?
It's more like a characteristic that's hidden.
Okay.
It's a property that we describe mathematically, but not visually.
Interesting. So the way we conceptualize things in quantum mechanics is already a major departure from classical physics.
Absolutely.
And this leads to another crucial difference: the relationship between states and measurements.
Right. So in classical mechanics, if you know the state of a system, like the position and momentum of a ball, you can measure it and you'll just confirm what you already knew.
Right.
Straightforward.
Yeah.
But in the quantum realm,
I'm sensing it's not so simple.
no, it's not so simple.
Yeah.
Measuring a quantum system actually disrupts it.
Wait, hold on. So you're saying just by looking at something,
Yeah.
we change it?
Yeah, you change it.
That doesn't make sense in my day-to-day life.
I know, it's one of the weird things about quantum mechanics, but that seems to be how it is.
Okay.
The book uses this thought experiment with a spin measuring apparatus.
Right.
So imagine a device that can measure whether an electron's spin is up or down along a chosen axis.
All right, I'm picturing it.
Okay.
So in classical physics, the electron's spin component along a particular axis should be fixed, right?
That's right.
Measure it once, you get a result.
Yes.
Measure it again, you get the same result.
That's what you'd think.
Yeah, but the
No.
quantum world,
Quantum world, different rules.
different rules.
Okay.
So if you measure the spin along one axis, let's say the x-axis, it randomizes the spin along the other axis, like the y and z axis.
So even if we knew the electron spin was up along the z-axis, the moment we measure it along the x-axis, that z-axis information is gone.
That's right.
It's like the act of measuring forces the electron to choose.
Yeah, it's like it has to make a choice.
And it wipes out the other information.
Yeah, it's a really strange thing.
Okay, so that's wild.
And that's what the book emphasizes.
Yeah.
That classical observations are gentle,
Mhm.
but quantum measurements are disruptive.
And this has implications. It even affects the logic that we use to understand the world.
What do you mean by that?
So imagine you want to confirm two statements. A, the electron spin is up along the z-axis.
All right.
And B, the electron spin is up along the x-axis.
All right.
Classically, no problem, you can confirm both of those statements
Yeah.
independently of each other.
That makes sense.
But in the quantum world, the act of confirming statement A by measuring along the z-axis actually disrupts the system.
Okay.
It makes it impossible to confirm statement B accurately.
So the very act of measuring one thing interferes with our ability to measure another.
Yeah, and that's why they had to develop a whole new way of describing things mathematically.
Okay.
And that's where complex numbers and state vectors come in.
All right. Now, I remember complex numbers from school, but how do they apply to quantum mechanics?
Well, they're essential because quantum states are represented by vectors,
Okay.
but not just any vectors. They're vectors in a complex vector space.
So these vectors, their components, can be complex numbers.
That's right.
Okay, this is getting abstract.
Yeah, it's a little bit abstract, but a good tangible example is continuous complex valued functions.
Okay.
They satisfy all the properties of a vector space.
So we're expanding our idea of what a vector space is
That's right, exactly.
beyond just, your typical three-dimensional vector.
Exactly. And then they introduce column vectors, which are just columns of numbers,
Okay.
and a notation called bracket notation, which is a shorthand for representing quantum states and operations.
Can you give me a sense of how that notation works?
Sure. Essentially, it involved representing states as vectors and operations as matrices.
Okay.
And matrix multiplication is how you combine these things.
So we're building up a mathematical toolbox here.
That's right.
What's next?
Next are operators and observables,
Oh, yeah.
which are central to quantum mechanics.
What's an observable?
An observable is something you can measure, like
Uh,
spin or position. And an operator is a mathematical object that represents an observable.
okay.
You can think of it as like a machine, like the book suggests.
Okay.
You feed it a vector, a state vector, and it spits out another state vector.
Okay.
And a special type of operator is a Hermitian operator.
Okay.
It has a very special property
Okay.
that it's its own Hermitian conjugate.
Okay.
But basically, Hermitian operators represent measurable quantities,
Okay.
and their eigenvalues, which is another important concept, are always real numbers.
Now, why is it important that they're real numbers?
Well, because when you measure something in the real world, you get a real number.
Right. Right.
You don't get an imaginary number. So this is how they connect the math to the physical world.
Right.
The fundamental theorem of quantum mechanics, which sounds very scary,
Right.
is actually quite simple.
Okay.
The eigenvectors of a Hermitian operator form a complete set.
What does that mean?
It means any quantum state, no matter how complicated it is,
Yeah.
can be expressed as a combination of the eigenstates.
So they're like the building blocks.
They're like building blocks.
Yeah.
And the book then goes on to lay out 4 fundamental principles that govern quantum systems.
All right. Let's hear them.
Okay, so principle number 1. Observables are represented by linear operators.
Okay. That's a good starting point.
Okay, number 2. The possible results of a measurement are the eigenvalues of the operator.
So eigenvalues are all the different readings you could possibly get.
Yes, exactly.
Got it.
Number 3. Distinguishable states are represented by orthogonal vectors.
So those are vectors that are pointing in completely different directions.
That's right.
Okay.
Okay, and then principle number 4. The probabilities of different outcomes are determined by something called the squared magnitude of overlaps between state vectors.
Okay, that's sounds a bit complicated, but what it's basically saying is that there's a way to calculate
Yeah.
the chance of getting your particular outcome.
Yeah, exactly.
Okay, so the book then applies these principles to the spin system that we've been talking about.
Yeah, and shows that you can represent these spin operators by matrices called Pauli matrices.
So the Pauli matrices are a tool that we can use to work with spin states.
Yeah, exactly.
Got it.
And then it leads to this very profound point that there's a fundamental difference between states and measurements in quantum mechanics.
So we can't just directly observe the state
Right.
like we can with a classical object.
Yeah,
Measuring a quantum system forces it to pick,
that's right.
and it wipes out information about other states.
Exactly.
Wow, it's like the observation itself is changing the reality
It's very, very strange.
that we're trying to measure.
Yeah, very strange.
So that's pretty mind-blowing.
It is mind-blowing.
But I'm ready for more.
Okay, good.
What's next on our quantum adventure?
Next, we'll delve into the concept of uncertainty and explore the uncertainty principle, one of the most famous ideas from quantum mechanics.
Okay, I'm definitely intrigued. I
Yeah.
can't wait to see where this journey takes us.
All right, let's go.
All right, so we've established that quantum mechanics is a whole different world compared to classical physics. We've got these mysterious quantum states, disruptive measurements, and even the logic we rely on starts to break down. What I'm curious about is how all of this connects to the familiar ideas of particles and waves.
That's a great question, and it's where things start to get really interesting. What's remarkable is how quantum mechanics beautifully merges these seemingly separate concepts. Up to this point in the book, particles and waves haven't been the main focus. This is where those ideas truly come to life.
So how does the book bridge this gap?
It starts by reminding us that the space of all possible wave functions is itself a vector space. This means we can apply all the powerful tools of linear algebra we've been discussing to understand how wave functions behave.
Okay, so wave functions are part of this mathematical framework we've been building. But how do they actually relate to particles?
This is where the probabilistic interpretation of quantum mechanics comes in. The wave function doesn't tell us exactly where a particle I, but rather it describes the probability of finding the particle at a given position.
So it's not that the particle is the wave, but rather the wave function gives us a sort of map of where the particle is most likely to be found.
Exactly. And this is a huge departure from classical physics where, in principle, we could know both the position and momentum of a particle with absolute certainty. In the quantum world, we have to embrace this inherent fuzziness, this cloud of possibilities.
It's like we're trading the deterministic certainty of classical physics for a world where chance and probability play a fundamental role.
Precisely. And the book goes on to introduce the momentum basis, which is another way of representing these quantum states, this time in terms of momentum rather than position.
So we can describe the state of a quantum system in terms of where it might be located, or how fast it's moving.
Yes. And the book introduces this really cool mathematical tool called the Fourier transform. It lets us seamlessly switch between the position and momentum representations of a wave function.
So it's like having two different languages to describe the same physical reality, each offering a unique perspective.
That's a great analogy. And through this lens, the book highlights a crucial relationship. Momentum is connected to wavelength. The higher the momentum of a particle, the shorter its wavelength.
Interesting. So a fast-moving particle has a shorter wavelength than a slower one. What are the implications of this connection?
This relationship has huge implications for how we study the microscopic world. Think about it. The smaller the object we want to examine, the higher the momentum and hence the energy of the particles we need to use.
So to investigate tiny particles, we need to use particles with a lot of energy to see them.
Exactly. That's why physicists have built these incredibly powerful particle accelerators. They smash particles together at tremendously high energies, allowing us to probe deeper and deeper into the subatomic realm.
It's like using a more powerful microscope to zoom in on the tiniest building blocks of the universe.
Precisely. And this leads us to the question of how these quantum particles move when forces are involved. The book delves into particle dynamics, starting with a review of the Hamiltonian. You might remember this concept from classical mechanics. It governs how a system changes over time based on its energy.
Right, the Hamiltonian gives us a way to describe the total energy of a system. But how does it apply in the quantum world?
Well, they begin with the simplest case, a free particle, a particle that's not subject to any forces. What's fascinating is that the quantum dynamics of a free particle actually line up with what we'd expect from classical motion. The average position of the particle moves in a straight line at a constant speed, just like in classical physics.
So even in the quantum realm, some things behave as we'd expect based on our everyday experience.
Yes, but there's a catch. While the average motion might look classical, the wave function itself can spread out over time. This spreading is a purely quantum effect, and it's not just a theoretical curiosity, it has real consequences.
What kind of consequences are we talking about?
The book explains how sudden changes in a potential, like encountering a barrier or a steep well, can cause these wave packets to break apart. This is something we wouldn't see in classical mechanics.
It's like a wave hitting a rock and scattering in multiple directions.
Exactly. This spreading and scattering of wave packets is a key characteristic of quantum behavior. And the book doesn't stop there. It delves into a really intriguing concept called path integrals. It's an alternate way of formulating quantum mechanics, one that focuses on entire histories rather than step-by-step changes.
So instead of thinking about a particle moving from point A to point B in a straightforward way, we consider all the possible paths it could take.
Yes, it's like imagining a particle exploring every possible route through a maze simultaneously. And each of these paths contributes to the overall probability amplitude, which determines the likelihood of the particle ending up at a certain point.
That's a really wild way to think about it. It's like the particle is somehow taking all paths at once, and these paths interfere with each other, like waves, to determine the final outcome.
Precisely. The path integral approach beautifully captures this wave-like interference, providing a deep and elegant way of understanding quantum phenomena.
All right, so we've gone from wave functions and probabilities to particle dynamics and these mind-bending path integrals. What's next on our quantum journey?
Now we're heading into the heart of quantum mechanics, the harmonic oscillator.
Okay, I remember the harmonic oscillator from physics class. It's that classic example of a mass on a spring oscillating back and forth. But how does it relate to quantum mechanics?
The harmonic oscillator isn't just a specific object. It's a fundamental concept that underpins a vast array of physical phenomena, from the vibrations of atoms in a molecule to the oscillations of electromagnetic fields.
So it's a much bigger idea than I initially thought.
It really is. And as the book eloquently explains, understanding the harmonic oscillator is crucial for grasping the essence of quantum field theory.
Quantum field theory, that sounds intimidating.
It is a complex subject, but it's the framework that describes all fundamental forces and particles in the universe. And the harmonic oscillator serves as a key building block in this framework.
So by understanding the harmonic oscillator, we're getting closer to understanding the universe at its most fundamental level.
Precisely. The book starts by laying out the classical picture of a mass attached to a spring, oscillating back and forth. They derive the equations that describe this motion, specifically the Lagrangian and the Hamiltonian.
Right, the Lagrangian and Hamiltonian provide different but equally valid ways of describing the energy of a system. But how do we transition from this classical picture to the quantum world?
That's where the magic of quantization comes in. We take the classical Hamiltonian and replace the position and momentum variables with their corresponding quantum operators.
Or those mathematical operators we talked about earlier.
Exactly. And by applying these operators to the wave function of a harmonic oscillator, we uncover something truly remarkable. The energy levels of the harmonic oscillator are quantized.
Okay, hold on. What does it mean for energy levels to be quantized?
It means that the energy of the oscillator can only take on specific, discrete values. It's not a smooth continuum like in classical physics. It's like climbing a staircase. You can only be on one step at a time, not in between.
So the energy of the harmonic oscillator can only jump between these distinct energy levels. That's a pretty big departure from classical physics.
It is. And the spacing between these energy levels is determined by Planck's constant, that tiny but all-important constant that governs the quantum world.
So even in this simple system of a mass on a spring, we're seeing the fingerprints of quantum mechanics.
Exactly. The book then dives into the math, solving the Schrödinger equation for the harmonic oscillator and deriving the energy eigenfunctions and their corresponding eigenvalues. These eigenfunctions are special wave functions that describe the states of the oscillator with definite energies, and they reveal some pretty fascinating features.
Like what? What's so special about these eigenfunctions?
Yeah. Well, for one, they oscillate like waves, but their amplitudes decay rapidly as you move away from the center of the potential well. This means that the particle is most likely to be found near the equilibrium position of the spring.
So it's like the particle is drawn to the center, but there's still a chance it could be found further out.
Exactly. And this brings us to another mind-boggling quantum phenomenon, tunneling.
Tunneling. Okay, I'm intrigued. What's that all about?
Even if the particle doesn't have enough energy from a classical standpoint to escape the potential well created by the spring, its wave function can extend beyond the boundaries. This means there's a small but finite probability of finding the particle outside the well, as if it tunneled through a barrier it shouldn't be able to cross.
Well, that's like something out of a science fiction movie.
It is. Tunneling is a purely quantum effect, and it has profound implications for many physical processes, from nuclear fusion in stars to the operation of transistors in our everyday electronics.
So the harmonic oscillator isn't just a simple textbook example. It's a gateway to understanding some of the most profound and counterintuitive aspects of quantum mechanics. We're seeing quantized energy levels, wave-particle duality, and now this incredible phenomenon of tunneling.
You're getting it. The harmonic oscillator really is a window into the deep structure of the quantum world, and the book goes on to connect this quantization of energy in the harmonic oscillator to the concept of photons as particles of light.
Right. We were talking earlier about how light can behave as both a wave and a particle. How does the harmonic oscillator help explain this?
Well, imagine a cavity, basically a box with perfectly reflecting walls. The electromagnetic radiation inside this cavity can be described as a collection of harmonic oscillators, each corresponding to a different wavelength of light.
So we're using the harmonic oscillator model to describe light trapped within this box.
Precisely. And remember how the energy levels of the harmonic oscillator are quantized? Well, that means the energy of the electromagnetic radiation in the cavity is also quantized. It can only exist in discrete packets of energy.
And these packets of energy are what we call photons.
Exactly. So a beam of light can be thought of as a stream of these photons, each carrying a specific amount of energy determined by its frequency.
That's amazing. It's like light is made up of these tiny bundles of energy, and the harmonic oscillator gives us the theoretical framework to understand how these bundles behave.
Precisely. This connection between the harmonic oscillator and photons is a profound insight that bridges the gap between classical and quantum descriptions of light.
So we've come a long way in this deep dive. We've gone from the counterintuitive nature of quantum measurements to the merging of particles and waves. And now we've seen how a simple system like the harmonic oscillator can unlock some of the deepest mysteries of the universe.
We've definitely covered a lot of ground. What are your thoughts so far? Does anything stand out to you as particularly surprising or intriguing?
Honestly, it's all pretty mind-blowing. I think what strikes me the most is how quantum mechanics forces us to rethink our basic assumptions about reality. It's a world where certainty gives way to probability, where measurement disrupts the very thing we're trying to observe, and where particles can seemingly tunnel through impenetrable barriers.
You've hit the nail on the head. Quantum mechanics is a radical departure from our everyday experience, and yet it's the most accurate description we have of the universe at its most fundamental level.
Well, I'm definitely eager to keep exploring this strange and fascinating quantum realm. Where do we go from here?
In the final part of our deep dive, we'll tackle another mind-bending concept, entanglement, and we'll touch on the implications of quantum mechanics for understanding the entire universe.
Okay, I'm ready. Let's dive into entanglement.
Okay, I'm ready. Let's dive into entanglement.
All right, so entanglement, it's one of the most bizarre and fascinating aspects of quantum mechanics. It's where two or more particles become linked,
Okay.
and the way that their fates are intertwined, even if they're separated by vast distances. Okay, that sounds pretty wild. Can you give me an example?
Sure, imagine two electrons that are entangled. If we measure the spin of one electron and find it to be up, we instantly know that the spin of the other electron must be down, even if those electrons are miles apart.
Wait, are you saying that measuring one particle instantly affects the state of the other,
It seems that way.
regardless of the distance between them? That seems to violate the idea that nothing can travel faster than the speed of light.
Yeah, it's incredibly counterintuitive.
Yeah.
And it's one of the reasons why entanglement has been a subject of intense debate and research for decades.
So how do we even begin to explain this?
Well, the book uses a thought experiment
Yeah.
involving two characters,
Okay.
Alice and Bob.
Okay.
Each receives one particle from a pair
Okay.
that's prepared in a special entangled state called the singlet state.
So Alice and Bob each have one of these entangled particles.
Yes.
What's special about the singlet state?
It represents the ultimate form of entanglement. No matter which axis Alice chooses to measure the spin of her particle along, Bob's particle will always be found to have the opposite spin.
So if one is heads, the other one is tails,
Yeah.
no matter how far apart they are.
Exactly.
But how is that even possible?
That's the mystery of entanglement.
Yeah.
The correlations we see between entangled particles can't be explained by any classical mechanism.
So entanglement is real,
It's a real phenomenon.
even if we don't fully understand how it works.
It's been experimentally confirmed many, many times.
Okay, so this is like legit, this is happening.
It's happening.
Wow.
It's one of the most profound and puzzling features of quantum mechanics.
Okay.
And it has far-reaching implications.
Like what?
Not just for our understanding of the fundamental nature of reality, but also for the development of new technologies like quantum computing.
How does entanglement play a role in quantum computing?
Well, entanglement is one of the key resources that allows quantum computers to perform calculations that are impossible for classical computers.
So this bizarre quantum phenomenon could have a huge impact on our future.
It very well could.
Oh.
And it all stems from these fundamental principles of quantum mechanics that we've been exploring.
So we've journeyed from the counterintuitive nature of quantum measurements to the wave-particle duality of matter, and now to this mind-boggling phenomenon of entanglement. It's been quite a ride.
It has been quite a ride, hasn't it?
It has. You know, quantum mechanics, it's a field that forces us to rethink our basic assumptions about reality. It's a world where certainty gives way to probability, where measurement disrupts the very thing we're trying to observe, and where particles can seemingly tunnel through impenetrable barriers. So to wrap things up, I want to thank you for guiding us through this deep dive into quantum mechanics. It's been a truly illuminating experience, and I'm sure our listener feels the same way.
It's been my pleasure. And remember, the quantum world is full of surprises, so keep exploring, keep questioning, and who knows, maybe you'll be the one to make the next groundbreaking discovery in this fascinating field.
Loved this video? Smash that like button and subscribe so you don't miss out on future content. And don't forget to order the book. Link below.